Hello everyone, welcome to lecture 31 in this course Diffusion in Solids. So far we have talked in first few weeks on solution to diffusion equations. Then we also saw the atomic mechanisms related to diffusion, and we also in the last couple of weeks talked about the aspects of interdiffusion. Now, one of the things is that when you talk about the diffusion control process, we know that the diffusion rates in solids are typically lesser when it is compared to liquids or in gases, and that's why, and given the nature of the so many complex phases that can form, and you have so many material combinations, the phases are a function of temperature, compositions, and so on. So, a lot of time it is not possible to do everything experimentally. Okay. So, if I want to study, let us say, phase growth like we saw in the previous lectures, then some experiments definitely I can carry out, but then there are certain phases which I cannot capture during my experiments, because either the rate may be sluggish or the temperatures required are too high, and several other reasons. So, therefore, now increasingly people have started looking on predicting the diffusion profiles, or on predicting, let us say, the phase growth, or predicting how the, if I join A and B, how will the interdiffusion zone develop. Okay. Or if I am having a certain diffusion problem, what kind of solutions I can expect. So, all these material processes now people want to predict using the thermodynamic modeling. That is one way of prediction, the computational tools that people want to use. So, I thought that I will give you a glimpse of these computational tools in this week's lecture. Of course, there are dedicated courses which deal in detail about the computational techniques for thermodynamics, for kinetics, and so on. But this would be a basic introduction to this field, and those who are interested can take up more related course in detail. So, when it comes to the thermodynamic modeling or the prediction, the approach that is used is known as CALPHAD. I will shortly tell you what this CALPHAD stands for. So, in this week we will first talk about this approach in today's lecture, that what is CALPHAD, what is the principle of CALPHAD. Then in the next lecture I will introduce you to some of the softwares and the modules within them which are popularly used for phase predictions and doing the kinetic simulations. Then the following lecture would cover the important aspects of the databases that are used for predictions. Then we will solve a couple of problems using this computational tool. I will give you a demo, and the week will end with the tutorial lecture as always. So, today we are going to talk about what is actually this CALPHAD. So, let us start. So, you know, we have all seen this even when we were revising, and otherwise also you know that this is what we know as a phase diagram. Now, when we were talking about or when we were revisiting the thermodynamic concepts, I emphasized that there is one-to-one correlation between a free energy curve and a phase diagram. Remember that the phase diagram are the equilibrium plots, so as the free energy versus x, and there is one-to-one correlation between them. So, at this temperature, if I want to draw a free energy curve, it would look something like this, where you have a alpha, you have L, and you have a region alpha plus L. So, every point on the G versus X has a corresponding point on phase diagram, and vice versa. So, now phase diagrams, we know that they are very important for the material scientists and engineers to understand the relationship between composition, microstructure, and process conditions and the material properties sometimes, that is the indirect linkage. But a lot of material design, alloy design happens with the knowledge of phase diagrams. Now, the question is, how do you generate these phase diagrams? Because now with more and more new materials being used, more and more domains of existing system being utilized, how do we generate these phase diagrams? A lot of multi-component alloys now are being used in several applications. So, how do we generate these phase diagrams? So, experimental phase diagram determination, that is the traditional way, and that is a powerful way also, but a long and a tedious way nonetheless, which involves a multi-step process combining composition, annealing duration and thorough microstructure analysis. But not all the regions of all the phase diagram can be experimentally measured. There are some phase diagrams which are, for example, very almost the entire phase diagram is well studied through experiments, and all the regions are clearly identified. This is more true for the binary phase diagrams. But even in binary, there are certain phase diagrams, or there are certain regions in certain phase diagrams which are not accurately determined. The moment you go from binary to even ternary, you will see that there is a drastic decrease in the phase diagram that are experimentally obtained, because then the number of experiments or the number of variables that you need to take care increases manifold. So, therefore, experimental determination has certain limitations. And as I said, now if you go for higher order systems, the experimental determination become less and less feasible. So, theoretical routes are what people try to look at, which can help you generate these phase diagrams by using some computational techniques. So, this theoretical phase diagram construction basically relies on the principles of thermodynamics. And as I told that because there is a correspondence with the free energy versus composition curves, so the basis of generating phase diagrams is through the relationship between the G versus X curves and the corresponding phase diagrams. So, these equilibrium states are modeled using thermodynamic functions of temperature, pressure and composition. And that is used basically to simulate multi-component, multi-phase systems in complex materials. So, the modern approach is what is in the title is known as CALPHAD, which stands for calculation of phase diagrams. That is the widely used approach for thermodynamic modeling and phase diagram prediction. Now, what is this CALPHAD? So, as I said, that CALPHAD stands for calculation of phase diagram. So, you can see how it is abbreviated. It utilizes the Gibbs free energy as a function of composition, temperature, pressure and other atomistic contributions such as magnetism. See, one thing that should be intuitively clear to you, when we talked about the free energy versus composition diagram and their correspondence with the phase diagram, what we say always that the phase which has the minimum Gibbs free energy is the stable phase. For example, just let us say here, if you are here somewhere in this regime, then any point on if you draw a vertical line here, and the free energy at this composition is minimum for alpha than for the liquid. So, here therefore, you have the alpha phase as the stable phase. When you are in this region here, then there is a common tangent which has actually a lower which represents a lower Gibbs free energy than single phase alpha or a single phase liquid. So, that is why you see that the minimum Gibbs free energy exists for a mixture of solid and liquid, and that is exactly the phase that you observe in the phase diagram. So, it means that the thermodynamic equilibrium demands the minimization of the Gibbs free energy, and that is exactly the principle that is underlying for the CALPHAD approach. So, it generates what it tries to do, it generates thermodynamic descriptions of all phases based on their Gibbs energy. It's a very powerful method where Gibbs free energies are modeled, and their derivatives provide key thermodynamic parameters such as chemical potentials and thermodynamic factor for even diffusion simulations. Remember this word thermodynamic factor, we saw it when we were seeing the Darkins analysis and how the tracer diffusion coefficients are related to the intrinsic diffusivities. So, the thermodynamic models used by CALPHAD contain adjustable parameters which can be optimized to reproduce a wide range of experimental data and theoretical models, including first principle results. So, again for the prediction you need certain data which already exists. So, it is not to say that definitely the experimental results are very important. Based on the experimental results only the reliable models can be built, and then the available set of with the available set of experimental results you create your models and use them to predict the conditions which have not been done experimentally. So, this makes CALPHAD a versatile tool for predicting phase equilibria, simulating phase transformations and designing complex multi-component materials. A little bit about history of CALPHAD. As long ago as 1908, phase diagrams was first calculated from Gibbs energy models by Van Laar. Then Larry Kaufman wrote the first general description of CALPHAD in the book Computer Calculations of Phase Diagrams. That was in 1970. Then Kaufman also introduced the concept of lattice stability. He demonstrated how thermodynamic parameters could be derived from both experimental phase diagrams and early first principle techniques. It laid the foundation for using these parameters to calculate the phase diagrams. It is important to see what parameters I should calculate which will help me in predicting the phase diagrams. So, originally CALPHAD focused on calculating phase diagrams by adjusting thermodynamic models to match the experimental data. Okay, so earlier what CALPHAD focus of the CALPHAD was that you basically calculate phase diagrams by adjusting your thermodynamic models such that it matches the experimental data. Today, CALPHAD actually encompasses selecting models for the phases that can be extrapolated across composition and temperature ranges, even including the metastable region. You mean what it means is that earlier, suppose I have a certain set of experimental data. Now I create a thermodynamic model, and that model then I validate and see that my experimental data is validated. That means it was only confined to the available experimental data. But now, after so much of refinement and so much of work has gone into this, that the available data, with the help of the available data, the CALPHAD approach, you can extrapolate and predict the phases which are not experimentally determined. You can go beyond the composition that are studied using the experimental phases. You can even also try to predict the metastable regions which are not always experimentally visible, and so on. Now, the components of CALPHAD, they refer to the essential elements and the systems that make up its framework for modeling and predicting phase diagrams and thermodynamic properties. So, the first key component is the experimental data. Now, you may see that sir, it sounds a little contradictory, but it is not contradictory. It is, as I said, that your experimental data is the basis on which you can basically generate your models. The validation of your models actually can be done by using the experimental data. Okay, that is one thing. So, the type of experimental data includes the phase equilibrium data, that means information on phase boundaries and compositions at specific conditions, thermodynamic properties, enthalpy, entropy, heat capacity, etc., activity and partial molar properties, which tells you about the solution behaviors, whether it's ideal, non-ideal, and the phase transformation data. This is critical for validating the predicting phase diagrams. So, because for example, if you have a completely unknown system and you predict, you want to predict, then it is very challenging. Whereas, when you have certain data that is already available, that can form the foundation for let's say generating the rest of the data pertaining to that system. So, experimental data is very crucial component of CALPHAD. It is the foundation for the CALPHAD. Then comes the thermodynamic models. They are also central to the CALPHAD. They represent the Gibbs free energy of phases as functions of temperature, pressure and composition. And there are different thermodynamic models. First is pure substance models. That means they describe the elemental Gibbs free energy, the pure elements Gibbs energy. Solution phase model, they capture the mixing behavior, ideal, regular, subregular and so on. Ordered phase model, because not all phases are solid solution phases, there are certain ordered structures which are also possible. So, there comes the sublattice models for intermetallic compounds. You have gas phase models, ideal and non-ideal gas mixtures. Then you have magnetic models which include contributions from the magnetic order. Then the third important component is the Gibbs energy minimization. So, the stable phases at any given conditions are determined by minimizing the Gibbs energy of the systems, and then using numerical algorithms to balance phase fractions and compositions under the thermodynamic equilibrium. This Gibbs free energy minimization is carried out. The fourth important component is the optimization tools. These tools fit the model parameters to the experimental data. So, there are optimization software which adjusts interaction parameters, phase properties, etc. Because once you have a model, you try to fit the model, then you see whether it can predict and how well it agrees to your experimental data that is available. Sometimes even the output of the model, does it make a physical significance or not. And suppose if it does not make a physical significance, or if it is too much deviating from what is observed experimentally, then you need to tweak your model, you need to optimize certain parameters to improve the predictability, reliability of your model. So, the optimization tools are also very important, and these iterative processes, they ensure that the model reproduce the observed behavior accurately. Now, let us try to look at some aspects of the thermodynamic models of CALPHAD. So, the very basic equation is this free energy equation where G is equal to H minus Ts. So, here as I already said that it implies a variety of mathematical models to describe Gibbs energy of individual phases in a systems. So, this what I have written is actually for the pure substance for which the Gibbs energy is expressed as a function of temperature and pressure. H is equal to enthalpy at the temperature T and S is entropy at the temperature T. Then solution phases which describe mixtures of components such as liquid and solid solution, their Gibbs energy is expressed as G is equal to summation xi gi naught plus RT xi ln xi plus G xs. Now, here you look carefully that these are the terms when we saw the thermodynamic revision lecture, there we already saw that for example, when you consider the ideal solid solution, you had in the overall, remember this is not just the mixing energy, this is the total free energy of the solution. So, you had this term like XAGA plus XBGB. So, that if you extend for n component system, you can write it as summation of xi gi naught, because gi naught is the Gibbs energy of the pure component I. Then you have this term which is like ideal mixing entropy plus RT summation xi ln xi. So, this is present for ideal solution, we saw it for regular solution and so on. Then there is a term which is Gxs. So, this Gxs is the additional contribution which is also representing the deviation from ideality. For example, when you had this regular solid solution, this term was simply equal to omega xa xb. Okay. Subregular solution model, it will be something else. Similarly, any other solution model, this term will be always there, which is the pure elements free energy, then a configurational entropy of the ideal solution, and then the excess free energy term. So, this excess Gibbs free energy is modeled using a regular solution model, subregular solution model, etc. This is the excess term is what we are to we usually worry about. So, as I already said that excess Gibbs energy models include the regular solution model where Gxs is written as summation xi xj lij, which is interaction parameter between components I and j. So, this assumes a symmetric mixing behavior. So, earlier we talked about only binary system, but here now this can be generalized for systems with the n number of components. Subregular solution model, it includes the composition dependent interaction parameters. Remember, when we talked about the omega in the case of binary system, omega is independent of the composition when it comes to the regular solution model. In the subregular solution model, the composition dependence of omega is also taken into account. So, therefore, the Gxs is written something like this, summation xi xj lij naught plus lij1 xi minus xj. Then you have Redlich-Kister polynomial, which is widely used for asymmetric mixing, where Gxs is given by summation xi xj multiplied by summation lij xi minus xj to the power k. For ordered phases, then we use what is known as compound energy formalism, which describes ordered phases with multiple sublattice, and each sublattice can accommodate specific elements or species. So, this formulation looks something like this, where Ys represent the side fraction of species S. Then the CALPHAD thermodynamic models also include models for magnetic contribution. They are modeled to account for the effect of magnetism on the Gibbs energy, and this is particularly important for phases like ferrite or austenite in iron carbon system. The magnetic free energy is written as minus RT ln beta, where beta represents the magnetic order parameter, which depends upon the Curie or the Néel temperature. So, specialized software that are used to implement CALPHAD approach include ThermoCalc, FactSage, Pandat, OpenCALPHAD. We will try to give you some description of one or two of these softwares in the upcoming lectures. So, the advantage of CALPHAD include the predictive power for complex systems, it is accurate and reliable, integration of the kinetic data, then reduction of experimental work, accelerated material design and discovery. This is very important now, because if you want to develop a new alloy, let us say you want to add a certain third element to an existing binary alloy or a fifth element to an existing fourth component alloy, how much the element to be added, what will be the impact, what are the new phases that are going to form if I add that element. So, if you try to do this experimentally, it consumes a lot of time, whereas with CALPHAD this workload of experiment can be significantly reduced. Then you have flexibility across material systems, and it can be adapted to new methods. Limitations, it depends on the quality of the experimental data. Sometimes there are exploration issues as well, and the calibration and the maintenance of database is also one of the tedious task, because we will see later that databases are the foundation on which the thermodynamic models are built. So, if you need to regularly update this databases, and then quality of experimental data is also very, very important. But applications of CALPHADs are huge, which range from prediction of phase diagrams to doing the kinetic simulations, materials design, process simulations, and so on. So, there are a lot of applications for CALPHAD models for materials and for other applications as well. Recently, now people are trying to integrate the machine learning with CALPHAD to develop more robust and develop new thermodynamic model. It is also being tried to use in multiphysics simulations. And in the future directions, the plan is to integrate it with AI and data-driven approaches. Expansion of material property databases are required. That means whatever the databases that are available now, the goal is to increase those databases, and then application to the emerging materials such as quantum materials and the very advanced materials where the CALPHAD also is being looked forward to. So, this is a brief introduction to the CALPHAD. Here are the references from which some of the information used in these slides and the data presented has been taken. In the next lecture, I will try to show you some software which are very useful for which applies the CALPHAD approach and are very useful for predicting the phases and doing the kinetic simulations and so on. So, thank you. See you next week.